Right, so basically what we wanted to do here was take wind energy and convert it into a usable source through a USB port. Because there's a lot of devices out there that are powered by USB, like cell phones and things like that, so we figured it would be really convenient if we could do that. So what we started off with was basically taking a 24-volt DC PC fan and running it in reverse, which gave us an AC output that we ran through a rectifier, which turned that basically into like a DC voltage source coming through this. Then from that point, we stored it in a capacitor bank and then allowed that to charge, and then it would discharge, and then we regulated that output to 5 volts. So pretty much once we had that system designed, what we started doing was figuring out what kind of wind speeds we needed. And so we originally wanted the system to work at about 10 miles per hour. So for that case, average in Raleigh, for instance, which is where we've done all our testing, is about 8 to 10 different parts of the year. So we ran all our tests at 10, and we get fairly high voltages out of about 11 volts, which with about 30 milliamps, which is enough to actually charge most devices and things like that. But because we had to regulate that, considering you can't give devices more than 5 volts, the regulator actually ended up dropping about 30% of our overall input voltage. So it dropped way lower, and so while the system can still operate at 10 miles per hour, the current is just so low that the charge times are almost negligible for what you would actually be useful for. So we ended up determining that between the 13 mile per hour and 15 mile per hour wind speed is what we start getting efficient output for. And then at that point we started charging. We've done different things. You can plug the phone in directly, but the way they charge is a much slower charge. So we actually found these small battery packs here, which they're designed to take a USB charge and store it for a while, and then it's portable and you can plug it in there. And these actually are very good at trickle charging, so they charge small currents, can charge them over a while. So at 15 miles per hour, we ran this for an hour, and was able to get enough of a charge through this to turn on this particular phone, which is not an EVOS, but it's an HTC smartphone. And was able to turn that phone on and run it for about 5 minutes. So what we're kind of gearing this towards right now is a emergency type system. So if you know, you're stranded somewhere, or if you're out camping or something, you don't have a constant supply of power from a car or anything like that, then you can still make an emergency phone call or something, because 5 minutes is long enough to turn the phone on and make a call for that way. We have different ways of making the system more efficient that we've known before. The voltage regulator obviously being our most efficient portion. If that was replaced with a buck boost converter or anything or something along those lines, we drop much less current through there and it becomes much more efficient. We looked into it, but we weren't able to actually find a particular system that would match ours well enough, just already pre-packaged to work. So given the time constraints during this semester, we just went with the voltage regulator. Also, another design is actually putting an oscillator in this system that switches the power to that capacitor bank over time, generally 25 to 30 times a second. And what that would do is actually allow that full voltage to go across the capacitors and charge up, and then it discharges at that higher voltage, because the discharge is much higher than the constant charge rate. And so it wouldn't be a constant charge technically, but 25, 30 times per second, so a normal human wouldn't be able to tell the difference, and most devices wouldn't. It would look like a constant charge. And at that point, the efficiencies would be high enough to make this almost useful for recreational purposes. So at 15 miles per hour, you start looking at charge times around 25, 30 minutes to get a fairly decent charge on your phone. So if it's already down to half charge, you can get back to 3/4 in 25, 30 minutes. So, and that's pretty much the basics of our project. Well, for the future, what we wanted to do was make it more of a energy harvesting device instead of pigeonholing it to one thing like wind. So we looked through different ideas, such as a hand crank generator, solar power, and then also like water turbine, so if you're next to a stream or something like that. And so we came up with designs, and we went ahead and implemented the solar panel design, because of being one of the easiest ones. And this particular solar panel here will actually produce 18 volts, about an amp, given full direct sunlight. So there's enough power just from the solar panels to actually charge a car battery. We don't have the leads set up for it or anything like that, but it's more than enough power. And the way we wired it into the circuit, they actually operate in conjunction. So you can either run wind by itself and get power, run solar by itself and get power, or run both at the same time and get the power from both of these. And so we designed this in such a way so that in the future, all the other elements like the hand crank generator and things like that are plug and play. So you just unplug the wind, and plug in like the hand crank. So that way, if you're going somewhere and you know the conditions of that area, you can plan ahead in advance, and you always have some sort of power to go along with, and it would be compact and portable. So that being said, this particular system, the prototype, paying full retail price for everything, ran us about $110. But without the markups, it would have been about $60, and of course manufacturing would drop that down to about $25. And at that rate, you could actually sell this retail at about $50, which makes it well within the price range of, most people considering this alone was $50 if you were to go buy an energy storage device. So we think it's really feasible, and it's gotten a lot of good attention so far. So.